With our discussion, and in this video we're going to discuss about your electric flux, and then we go through your Gauss's law. But before going to your Gauss's law and then your electric flux, let's first discuss your electric field of a continuous charge distribution, and later you will see why your Gauss's law is very nice, especially in solving electric fields, which involves charge distribution, which has symmetry in their shapes. Now, when a charge is distributed along a line, over a surface, or through a volume, few additional terms are useful. Since it's not always the case that you have your point charges, it's not always the case that we look for your electric field for point charges. So you also have your line charge, like say for example this one here. This is a line which is maybe positively charged or negatively charged. And then you have a sheet or a surface, and you may also have some volume charge. Okay, now from your superposition principle, if you have let's say if you have hundreds of point charges, you can still find the electric field at some field point by just summing your individual contributions of your charges, the individual field contributions of your charges. So it's just your electric field is just equal to your K times the summation of your Qi Ri squared Ri hat, where your I is the number of your source charges. Okay, this is the case for your point charges. But what if you have your line charge, or what if you have your surface charge or your volume charge? Of course, we do not know how many charges this line here is composed, or even this sheet here is composed. So what we can do here is we divide this one. Let's take this one, this line charge. We take some small line segment, okay, and let's say that this line segment DL, okay, has a charge DQ. Later you'll see this, you'll know what this lambda and then this sigma are, okay. So let's just take some small line segment around here, and then let's take this the charge of this line segment to be dq. And if you take the limit of your, and you know you can make again, and we can what I mean is, and you know that we can take as many line segments around here of infinitesimal length dl. And if you're going to sum up those line segments of charge dq, you have this one here, this sum here. And if we take this dq to be very, very small, so that the limit of that one will approach to 0, you have your k of the limit of delta qi to approach to 0 of this following sum here, your qi ri squared r hat. Now, in your calculus, in your Riemann sum integral, this sum here is just equal to this integral, k integral dq over r squared r hat. So for charge distributions for a line, for a surface, or for a volume, we can integrate this one from some initial and then final points. Okay, you integrate that one, and you can get your electric field for your charge distributions. Here, when a charge is distributed along a line, over a surface, or through a volume, a few additional terms are useful. For a line charge distribution, such as a long, thin charged plastic rod, you have your lambda for your linear charge density, and your lambda is equal to your Q over L, where your L is equal to your length. So here your Q is your charge, and then your L is your length. When a charge is distributed over a surface, such as a surface of imaging drum, you have your sigma for your surface charge density, which is equal to your Q over A, and then your A here is your area. And for a charge that is distributed through a volume, you have your rho for your volume charge density. You have your Q over V, and then your V here is for your volume. Okay? So you're going to use this one in order to solve for the electric field due to your continuous charge distributions. And let's have a quick example. Okay, So you have a field of a charge line segment. You have a positive charge Q that is distributed uniformly along the y-axis between y equals negative A and y equals positive A. Find the electric field at point P on the x-axis at a distance x from the origin. So you have here your line charge distributed uniformly along the y-axis from y equals negative A to y equals plus A. So what we do here is just we take again a small line segment of length dy or length dl, and then at this line segment here, infinitesimal line segment, you have your charge dq, infinitesimal charge dq. And then we take the contribution of this line segment, the electric field of this line segment at point P here, okay? And then we take another one. That is just what we do. We take another one, and then we also find for the electric field contribution of that line segment, and then we do another one, and then so on and so forth. But just from the previous discussion, this is just equal to your electric field here is just equal to your k times integral of dq over your r squared r hat. Okay, so we just integrate this line segment here to find the electric field at this point here. Now the solution of this one will look like this. Okay, so you have for your dAx and then dEy, these are the electric fields at the electric field components along the x-axis, and then the electric field component on the y-axis. And then we integrate this one. Okay, we integrate this one here, and then we get these answers. Okay, and then you also get these answers, which you can integrate using your integration table. But this is quite a tedious job to do. Okay, but the basic of this one is that you start with this one here. You take some dE, infinitesimal electric field, due to your dq, and then you get your x components and then your y components of your electric field. Do some integration, and then you get your answers. And as you can see here, all the y contributions of your electric field just cancels out. Okay, so if you have another one here at the same location, so you have this one here, so you have your dEy here and then another dEx here, so this just cancels, so all your y electric fields will just cancel out, and you have here your final answer, which is just along the x-axis. Okay, so at point P here, due to this line charge here, the electric field that is experienced at this point here will point along the positive x-axis, and you get this answer from a very tedious solution. If instead you have if you want x to be very greater than a, meaning this x here is very far from your line charge, or if that's that one. If you want this one to be very greater than your a, the length a, you get this electric field. Meaning, if we are very far away from this line charge, like say for example at some kilometers from this line charge, what is experienced by the field point here is just something like a point charge, as you can see here. This is similar to the electric field of a point charge. If instead A is very greater than your x here, if A is greater than x, what happens is that you get this your answer. You have your lambda over 2 pi epsilon naught. Now, I want you to remember this one. Remember this answer. We're going to get the same answer using your Gauss's law later. And your Gauss's law is a simpler solution to problems involving continuous charge distributions. This one here, this is very tedious, of course, because of the integration. And we'll do a simpler solution of this one using your Gauss's law. So please remember this equation here. We'll get something similar to this one later. Okay. Now, what's Gauss's law? I've been talking about Gauss's laws, but what is it all about? Gauss's law can be used as an alternative procedure for calculating your electric fields. Gauss's law is based on the inverse square behavior of the electric force between point charges. And it is convenient for calculating the electric field of highly symmetric charge distributions. And Gauss's law is important in understanding and verifying the properties of conductors in electrostatic equilibrium. Now, how do we start with Gauss's law? So we start with your electric flux, okay? But before that, let's look at the box here and consider, or just imagine having an imaginary box of a noun charge. Well, we don't actually know if there is a charge here, okay? It's just a box and then there is something there. Now the question is, how are you going to know that there is indeed a charge here, or if there is no charge inside the box, okay? How are we going to know, again, how are we going to know if there is some plus charge here or there is no charge, okay, without opening the box? If you can remember our previous discussion, you can know that there is a charge here if this box here has some electric field, okay? And how do you know that this box here has some electric field? You can put here some test charge. Okay, now if this test charge experiences a repelling force, then you can tell that there is a positive charge inside the box. If instead the test charge experiences an attractive force, then maybe inside the box is a negative charge, right? So that's how we're going to test for the charge inside this imaginary box. Now, a charge distribution produces electric field E, and the E exerts a force on a test charge Q naught. So that is what we did. We placed a test charge outside the box, and the test charge experiences the force. If there's a force, then that means there is a test charge, or there is a source charge inside the box. Okay, and by moving Q around a closed box that contains the charge distribution and measuring F, one can make a 3D map of your electric field, which is equal to your F over Q naught outside the box. And from that map, we can obtain the value of Q inside the box. So just like this one here. Now, positive charge within the box produces outward electric flux. So again, your charge is inside the box. Okay, we did not open the box; it's just inside the box, and there are electric field lines flowing out of the box. Okay, now. Positive charges within the box produces an electric flux through the surface of the box, and a negative charge produces an inward flux. Flux, when you're referring to flux, this comes from the Latin word meaning flow, meaning these are the flow of your electric field lines on the surface of the box. So for a positive charge inside the box, you have outward flux. Okay, if you double the charge inside the box, you have a double of your flux. If you have a negative charge inside the box, you have an inward flux. And if you double the negative charge inside the box, you have a double inward flux, meaning you double the flow, or there's a double flow of electric field lines inside or into the surface of your imaginary box. What's a zero net charge inside the box? Or what if we place a test charge here, and then your test charge does not experience some force? Does that really mean that there is no charge inside? Okay, so it's not always the case. So there are three cases in which there is a zero net charge inside the box and no net electric flux through the surface of the box. The first is there is really no charge inside the box. This one here, there's no charge here. So of course, there will be no flux for this box here because there is no charge inside. There's also a zero net charge inside the box if the inward flux cancels the outside flux, and that is possible if you have a positive and then a negative charge of the same magnitude. If you have this case here, the positive flux created by your positive charge is just cancelled by the inward flux of your negative charge. So if they are the same magnitude, then everything cancels out. If you put the test charge here, the test charge will not experience anything because there is a zero net charge inside your box here. And another one is there is no charge inside the box. Okay. If, let's say you have here your uniformly charged sheet. Okay. So there is zero flux here. If your flux or your charge is outside of the box. Okay. So you have this one outside of the box. So what happens here is that the flux created by your charge sheet, which goes inside, just goes outside. So what comes in comes out. So the flux is cancelled out. So these are the three cases wherein there is a zero net charge inside the box and no net electric flux through the surface. Okay. What affects the flux through a box? Okay. So as the figure shows below, doubling the charge within the box doubles the flux. So if we put more flux here from plus Q charge to plus 2Q charge, the number of flux doubles for a double charge. Okay, but if you double the size of the box, the flux does not change. So that means your flux is just dependent on what is inside here, not what the size of your box is. The net electric flux through the surface of the box is directly proportional to the magnitude of the net charge enclosed by the box. So it's just directly proportional to the magnitude of the net charge enclosed of the box. And it is independent of the size of the box. And actually, this is also independent of whatever shape your box is. So even if you have a circular, spherical container, not this box here, you still have the same flux because again your flux is just directly proportional to the magnitude of the net charge enclosed of the box. So meaning it's just dependent on what is inside. The flux is dependent on what is inside of your imaginary box, not on the size or the dimension or the shape of your box. What's electric flux? Electric flux is the product of the magnitude of the electric field and then the surface area A perpendicular to the field. Your electric flux is given by your raw E, that is your E dot A. And the units of your electric flux is in Newton dot meter squared per coulomb squared. So here you have your vector E, your electric field E, and then your vector A, the vector for your surface area. So again, your flux is just the number of electric field lines passing through a surface. So without the surface there is no such thing as a flux, but just your electric field lines. So it's the number of electric field lines passing through a surface. We can represent the direction of your vector A by using the unit vector n hat that is perpendicular to the area. So your vector A, you know the direction of your electric field. It's just radially outward for positive charges, radially inward for negative charges, or for a sheet you have this one. Okay. For a line charge you have, if this is your line, positive charges, the electric field is also radially outward. Okay, again this is radially outward because of the effects of the individual electric fields of your source charges. And you easily know the direction of your electric field, but what is the direction of your vector A? Now the direction of your vector A is the unit vector n hat perpendicular to the area. So if this is your area A here, okay, let's say this one here is your area A. Your unit vector n hat is perpendicular to the surface. So you have two. You have this perpendicular here, and then you also have the one at the back. Okay, you have two perpendicular at 90 degrees, okay, to your surface. It's just dependent on which side are you referring to. If instead your sheet or your area is lying down like this one here horizontally, your unit vector n hat is this one here perpendicular to your area. to your surface. So that is your N hat. As I've told you earlier, the electric flux is proportional to the number of electric field lines penetrating some surface. So it's the number of electric field lines passing through your surface. Okay, so if you're actually familiar with this one, if you look at your equation for your electric flux, your flux E is equal to your E, vector E, that's your vector A. If you know this dot product, you know that this is equal to your EA cosine theta. Because it's not always the case where in your your electric field and then your area are at 0 degrees or at angle degrees with respect to each other. There are instances where in your area is oriented at some angle theta, like this one here. You have some angle theta, so you use your EA cosine theta. The field lines may make some angle theta with the perpendicular to the surface, as I've said earlier. And if that is the case, you use your flux E is equal to your EA cosine theta, and your angle theta. This is the smaller angle between your E and then your A, always the smaller angle. Now, the flux is a maximum when the surface is perpendicular to the area of the field. What is meant of this one is that if your surface, say for example this one here, which is lying on the horizontal, and you have an electric field that is passing through this one, okay, your electric field are passing through that one. Okay. So you have your surface is perpendicular to the field. Now, since your surface is perpendicular to the field, you have an angle, or again here, your surface, this is your E lines, your electric field directions. Let me draw again your surface. Your vector A is this one here because you have here your your N hat perpendicular to your surface. As you can see here, your area vector and then your electric field vector are parallel. So you have here an angle that is equal to theta, or if these are anti-parallel, you have an angle of equal to 180 degrees. And for this case here, the flux is a maximum. Why is it a maximum? Because again, from your flux, you have your flux E is equal to your EA cosine theta. If theta is 0, your cosine theta is just 1. So you're just left with your EA. So it's a maximum. Now the flux is 0 when the surface is parallel to the field. So when the surface is parallel to the field, like say for example, again, you have the same surface lying on the horizontal, and then you have this field here flowing along the horizontal. Okay, so they are in the same, or your surface is lying on the horizontal, and then your electric field is flowing on the horizontal. That means your surface is parallel to the field. If you're going to look at the vector A, your vector A here is this one perpendicular to the surface, and then your electric field is this one here. If you see, your A and then your E are perpendicular at 90 degrees. So for this case here, the flux is 0. Why is it 0? Because your flux E, your EA cosine theta, your cosine 90 is 0. So this one goes to 0. Okay, your flux is maximum when you have this case here. You have your surface is perpendicular to the field. Your flux is 0 when your surface and your field are parallel. Now, if the field varies over the surface, you just use your EA cosine theta. This is valid only for a small element of area. So this is not a maximum because you have some values here that you multiply, some decimal values that you multiply to your EA. Now let us have an example. A disk of radius 0.10 meters is oriented with its normal unit vector n hat at 30 degrees to a uniform electric field E of magnitude 2 times 10 to the 3 Newton per coulomb. Since this isn't a closed surface, it has no inside or outside. That is why we must specify the direction of the n hat in the figure. So here, your disk is oriented in such a way that it makes that the n hat makes 30 degrees with respect to your electric field lines. Now here, your n hat is specified to be this one because, again, I've said earlier, there are two possible ways, or there are two n hat directions for this one. One is this one here, and then the other is below this one. So going here. So you're asked of the following items. A, what is the electric flux through the disk? B, what is the flux through the disk if it is torn so that n hat is perpendicular to E? And then, what is the flux through the disk if n hat is parallel to E? So we're going to torn your flux perpendicular and parallel to E. Now let's solve the problem. For A, you're asked for the flux through the disk. So this is A, the flux through the disk. So this is just your EA cosine theta. So we have your electric field E, which is equal to, you have 2.0 times 10 to the third power Newton per coulomb times the area. Since that is a disk, a circular disk, you have pi r squared, and then you have cosine 30 degrees. Theta is 30 degrees. And you just solve the area, and then you input the values in your calculator, and then you get an answer of flux, which is equal to 54 newtons that meters squared per coulomb squared for the flux. Now what happens for the flux if you're going to, or when n hat is perpendicular to E? So what happens with this one? That means your disk is rotated like this. So you have now here your perpendicular. Okay. So if that is the case, you have here theta, which is equal to 90 degrees, and your flux EA cosine 90 degrees. This is 0, so your flux here is 0. And then lastly, if you're going to rotate your disk such that your n hat is parallel to your E, so that means your disk will move like this, and your n hat now is parallel to your E. So you have theta is equal to 0. So you have the maximum flux. So your flux E is equal to your EA cosine 0. Cosine 0 is 1. So your flux E is just your EA. And you input the values, you get an answer of 63 Newton that meters squared per coulomb squared. And this is bigger than what we have in A, because here again, this is the case for when your flux is a maximum. Now, let's have a general general form of your flux. In the more general case, we look at a small area element. Just like we did earlier, we take some. Oh, by the way, this is for the case wherein your shape is irregular. Let's say, for example, this volume here. You have an irregular shape volume or area. Okay, you have this irregular shape. So, but you can still solve for the flux of this one just by taking some infinitesimal area, delta A. You make this area such that it appears to be a rectangle, and if that is the case, and if we take the limit of this area to approach to 0 so that it will be more near to being a rectangle, so the limit of your here we take the limit of your E dot A with your delta A approaches 0. This is just again from your calculus. So your delta E, your flux is now your integral of your E dot dA. So for your surface, for the flux of your surface, the surface integral means the integral must be evaluated over the surface in question. Like say for example around here, you integrate this one. In general, the value of the flux will depend both on the field pattern and on the surface. And if you want to learn more about this one, please review your calculus or study about the Riemann sum integral. Now let's try calculating the flux through a sphere. You have a point charge Q of 3 microcoulombs that is surrounded by an imaginary sphere of radius r, 0.20 meters centered on the charge. So this time our imaginary surface is a sphere, and then we surround your positive charge with this imaginary surface. And let's find for the flux for this one. Now your flux is just your EA, and your E is just your electric field for your point charge, which is equal to Q over 4 pi epsilon naught r squared. And the area for your sphere is your 4 pi r squared. And this 4 pi r squared cancels out, and you're left with this one here. Okay, and then having the values, you have your Q of 3 times 10 to the 6 coulombs, and then you have your epsilon naught, which is equal to 8.85 times 10 to the negative 12, and then you get this one here. We are actually interested with this one, Q dot epsilon naught, because from here you see that the flux is just actually dependent on the charge Q. As you can see, the shape of the sphere actually did not matter. It's just the flux is equal to your Q over your epsilon naught.